Hi, in this lecture, I would like to essentially just sort of show you a couple of other capacitor configurations or capacitor arrangements. The first one is called the coaxial cylinders case. So coaxial simply means I have two cylinders that share the same axis. So you can see it over here on the right. I've got an outer cylinder, which is a conductor, right? Capacitors are always made out of conductors. So I've got an outer conductor, which has a radius called B, and an inner conductor, which is a separate conductor, right? Insulated from the outer conductor is an inner conductor of a smaller radius A. So B is bigger than A. But more than that, actually, on this pair of conductors, each has the same length. So the lengths of the two cylinders is capital L. And this capacitance is, you can discover, right, that its value is 2 times pi times epsilon naught, L divided by the natural log of the ratio of B over A. The other capacitor configuration of two separate conductors is the concentric spheres. So you have an inner sphere, which I've drawn as a dotted line, and it's got a center right here. And you have this outer sphere, which is drawn with a solid black line. And they have two different radiuses. The inner sphere, the smaller radius, has radius A, and the outer sphere has radius B, where B is bigger than A. And the capacitance can be calculated to have this other functional form. 4 pi epsilon naught, you have the product of the two radiuses divided by the difference in the two radiuses, so the big radius minus the small radius. Right, so these are essentially instructions for how to calculate the capacitance. And remember that capacitance in both cases is simply the ratio of if you were to separate the charge Q between the two capacitors. You could imagine in the cylinder case, you could put the charge positive Q, let's say Q on the outside, and then on the inside, you smear the charge minus Q, right? So you separate the charge. And there's going to be an associated electric field between the inner negative conductor and the outer positive conductor that is the potential difference delta V. So there's going to be a potential difference between the inner conductor and the outer conductor, right? And likewise, the same case here. You could imagine separating the charge Q so that, let's say that the inner surface is caused to have a charge capital Q, which you took from the outer surface. So the outer surface has the negative Q. Then in between the two conductors is going to be an electric field, right? That's going to have some spherical symmetry. And that electric field can be associated with a potential difference between the inner conductor and the outer conductor. And that ratio of the charge separated divided by the potential difference between the conductors is going to have this value, right, in the sphere case. Okay, so you can read about these derivations, but I want to point out what you're going to see just in terms of a recipe. So the previous lecture, I think I used the word recipe in the title because this recipe is the instructions, right? And so the instructions that you're going to see, or the things that happen, are you start off by saying, imagine charge is separated, right? So In the sphere case, I called it capital Q. It doesn't really matter what its symbol is, but you imagine that the charge is separated. And this leads to electric field. And the thing is in this recipe, you actually have to figure out the electric field function. You need to be able to write down how the electric field might vary over X position, or how the electric field might vary over radial position. And so these variations in the electric field, you get the electric field function by various means. Whoops. Including Gauss's law, right? So if you read about the derivation of these two capacitances, you're actually going to see a book make use of Gauss's law to determine the electric field. And in this case, cylinders and spheres tend to have radial electric fields. So you're going to have electric fields as a function of radial distance from the axis or from the center. So yeah, so you imagine a charge is separated, and because charge is separated, you're going to have electric field, but you have to figure out the function, the electric field function. That is, how does the electric field vary depending on how far away from the axis or center are you? And then once you find the electric field, you use the electric field function to calculate the potential difference between the two oppositely charged conductors, right? So you calculate this potential difference, and you're going to have, right, this is the last step in the recipe, so you will have a relationship between the charge separated, the potential difference, epsilon naught, and details about the conductor's shapes and separations, right? And from this, you can deduce the ratio of Q over delta V, and this, you'll just call it the capacitance. And that's what's going to happen if you follow through the derivations of both of these situations. Okay, so that being said, why don't we just mess around and calculate one of these things, just for fun. And further, so let's calculate a capacitance from some realistic data. All right, so realistic data, and you might wonder, like, what counts as realistic? Think of a circuit board, right? Circuit boards have small elements, right? Small circuit elements. And for example, one of the circuit elements on a circuit board is a capacitor, right? So remember that for a parallel plate capacitor, which I haven't mentioned yet, I didn't mention a parallel plate capacitor in this lecture yet, but let's start with that. So let's study a parallel plate capacitor for a second, right? And let's have a realistic one. So remember that we had this sort of approximation where the distance of separation between the two plates, so here's a plate and here's another plate, they each have area A, and we imagine them being separated by a distance d, right? So let's have a parallel plate capacitor where d is 1 micrometer, for example, right? So the distance of separation is 1 micrometer. And let's say the area is, say, 1 centimeter squared, right? Because areas are distance squared. So you could imagine these little areas as being a little 1 by 1 centimeter area, right? So 1 centimeter, 1 centimeter. And the capacitance that we got before, so the capacitance had the area on the top, and it had the distance on the bottom, and it had the epsilon naught, right? So remember that capacitors are going to have epsilon naught in it, and then details about the conductor's shapes and separations. And here it is. The capacitance has the area, it has the distance between them, and it has the epsilon naught. So if you calculate this for our problem, right, the area is 1 centimeter squared, the distance is 1 micrometer, and we've got epsilon naught left over. And epsilon naught, I always have to look this up, excuse me, I have to turn on my computer. Epsilon naught's value is 8.85 times 10 to the something. Where is it? So I just looked at it. Oh, here it is. Okay, so 8.85 times 10 to the negative 12. And then the units are coulombs squared per newtons times meters squared, right? So that's the epsilon naught. So let's just calculate this out. So I've got 1 centimeter squared and the 1 micrometer. So the ones are super easy. I'm going to have this 8.85, 10 to the minus 12. So I've got 8.85 times 10 to the minus 12. And then I've got centimeters squared over micrometers. And then I've got all these units, coulombs squared per newtons times meters squared, right? So let's go through. So centimeters squared, so 8.85 times 10 to the minus 12. Centimeters squared is 10 to the minus 2 meters, right? A centimeter is 10 to the minus 2 meters, but I want all of that squared, right? Because the area is 1 centimeter times 1 centimeter. So here's 1 centimeter times 1 centimeter. And then I divide by 10 to the minus 6 meters. And then I've got coulomb squared per newtons times meters squared. So 8.85 times 10 to the minus 12. So 10 to the minus 2 squared is 10 to the minus 4. 10 to the minus 6 on the bottom is 10 to the positive 6 on the top. And then I've got meters squared divided by meters. We'll have 1 unit of the meter on top, but then it's divided by meters squared over here. So in the end, I'm going to have coulomb squared per Newton meter, like this. So if I finish it out, it's 8.85. So 10 to the minus 12 times 10 to the minus 4 is 10 to the minus 16. 10 to the minus 16 times 10 to the positive 6 is 10 to the minus 10. So I get 8.85 times 10 to the minus 10. That's all the numbers. And the units are, so check this out. The Newton times the meter is the same thing as the joule. So remember, newtons is the SI unit of force, meters is the SI unit of distance. And the way that you do work is you use a force over a distance. So the SI unit of work is called the joule, and SI units always use factors of 1. So 1 Newton times a meter is 1 joule. So this is a joule on the bottom. But remember that a volt is a joule per coulomb. So what I'm going to do is I'm going to take these units and I'm going to imagine it being a coulomb times a coulomb per Newton times meter. And I'll recognize this thing as 1 over the volt. So this is 8.85 times 10 to the minus 10 coulombs per volt. But this is what we defined as being called the farad. So let me just replace it with the SI unit of capacitance. So in the previous lecture, I tried to indicate that realistic capacitances, ones that you're going to hold in your hand or put in a circuit, are actually some really small amount of farads. Can you see that that's what we got? We have a realistic, right, little capacitor, a pair of plates separated by a micrometer. They're each 1 centimeter in, on their edge, right? So that's a very realistic thing, and we come out with 8.85 times 10 to the minus 10. So I'm going to rewrite this as, for example, 0.885 times 10 to the minus 9 farads. This is 0.885 nanofarads, for example, right? And you can do this kind of stuff with these other expressions, right? So epsilon naught, 8.85 times 10 to the minus 12, right, with the SI units. And then you can imagine a little concentric spherical capacitor. You could choose, for example, the inner radius to be something realistic, like why don't we make it half a centimeter? And the outer radius to also be something realistic. Let's make it a little bit bigger, 3/4 of a centimeter, right? And you can imagine going through the process of getting the capacitance, and it's going to honestly be of a similar scale to this. It won't be the same value, of course, right? But you can see how this goes. The reason why the capacitances are going to be small is because epsilon naught is small, right? And it's just going to show up in all these capacitance calculations. Something that's really important to realize, again, for the parallel plate capacitor, remember the capacitance is got the area on top, it's got the separation distance below, right? And then multiplies epsilon naught. Notice if A is caused to grow, but D stays the same, you get more capacitance. But let's think about what more capacitance means. More capacitance means for the same potential difference, right? So same potential difference, you might think of this as the same effort, for the same effort, you can separate more charge. So you might say that the voltage is the effort, is the how hard you have to try to cause the charge separation. We'll say this a little bit more technically and confidently later, but you can separate more charge if you have more capacitance. Or you could say per voltage, it's easier to separate, or you can separate more charge, or something like that, right? So more capacitance. So if you have a pair of plates, so here's one plate, and it's separated by some small distance from another plate, right? And this is some area and some distance. If I was to be able to manage having, say, twice the area, right? I'm drawing two separate plates, so let me be really careful. So two separate plates, right? Separated by some vacuum. What I've done is I've doubled the area, but I kept the distance between them the same. I will be able to load, twice the charge for the same potential difference, right? So yeah, I think you can see what I mean. But this is an argument by proportionality, right? So if I was to double A, leave D the same, epsilon naught's a constant of nature that you can't make adjustments to, then the capacitance simply gets doubled. And if you have a doubled capacitance, then the charge you can separate doubles for the same voltage. Okay.